For the longest time, AI has been this thing stuck inside our computers, right? Getting amazing at language, at creating images, but now it's starting to get physical. It's learning to walk, to pick things out, to actually interact with our world. So let's get into it. This huge leap for AI and why the bridge between the digital world and the physical one is being built way faster than you might think.
So why this sudden rush to build robots? Well, it actually starts with a pretty basic economic problem. A recent McKinsey report uncovered something pretty staggering. In advanced economies, the gap between job openings and people available to work has just exploded. It's grown 4.2 times in just the last 10 years. We literally have more work that needs doing than people to do it.
And just look at where these shortages are. We're talking about hospitality, healthcare, construction, manufacturing. These are all jobs that need a physical presence. You need actual hands to build a house, to care for a patient, or to move a box from point A to point B. These are jobs that require interacting with the real world.
And that gets right to the heart of the matter. For all the incredible things a large language model can do, it can't stock a shelf, right? It can't operate a machine. So that begs the question. If our current AI is trapped behind a screen, what kind of new intelligence do we need to finally break it out?
You see, to operate in our world, an AI has to perceive it like we do. For a long time, AI models were kind of specialists. You had LLMs that were masters of text, you had vision transformers that could understand images. But to actually act in the world, you have to connect what you see with language. You need to understand both. And that's exactly where vision language models, or VLMs, enter the picture. Now, a vision language model isn't one specific thing. It's more like a whole category of AI. The main goal, its entire purpose, is to create a shared understanding, a bridge between what an AI sees with its cameras and the words we use to describe that scene. This is the tech that truly closes the gap. Okay, so how does it work? The magic behind it is a concept called the joint embedding space. Just think of it like a universal translator for the AI's brain. It's this mathematical map where the idea of an image and the idea of a word can be put right next to each other and mean the same thing.
Let me make this super simple. Think about the word apple. Right now, you've got a concept in your head.
Now look at this picture of an apple. It's a totally different kind of input, right? But it points to the exact same concept in your brain.
That's precisely what a VLM learns to do. In that joint embedding space, the mathematical code, the vector, for the word apple and the vector for the image of an apple are pushed so close together they become almost identical. The AI learns at a fundamental level that they mean the same thing. And that is the key to true understanding.
And once you can do that, you unlock some seriously cool abilities. A VLM can look at a photo and write a caption for it. You can type a description and it'll find the exact image you're thinking of. It can even answer questions about what it's seeing. But the most exciting one for us, vision, language, action, using this deep understanding to actually power physical robots.
Which, of course, brings us right back to our main challenge. It's one thing to have an AI that can understand the world. It's another thing entirely to give it a body so it can act in that world. How do you actually go about building a physical AI?
So let's look at a really concrete example, NVIDIA's Project GROOT. Now, a ton of companies are tackling this. Tesla, Figure, Boston Dynamics, you name it. But GROOT is a great example of a specific approach, trying to create a single general-purpose foundation model that can act as the brain for lots of different kinds of robot bodies. So, building an AI like GR00T basically follows this three-stage life cycle. First, you have to generate a mind-boggling amount of data, everything from watching humans do things to running millions of trials in a simulation. Second, you do the training, where the model learns from all that data on massive supercomputers. And finally, you deploy a smaller, faster version of that model directly onto the robot so it can think for itself.
But here's the thing. That first step, getting the data, is the single biggest problem in robotics. I mean, there's no internet of robot actions for it to learn from. So the solution is the strategy called the data pyramid. The base is huge, tons of data from simulations and internet videos. But that stuff isn't always perfect. The real secret sauce is that tiny little tip of the pyramid, a small amount of really expensive, high-quality data from a real robot doing things in the real world. That's what grounds the whole model in reality.
The way the model itself is designed is actually inspired by the book Thinking Fast and Slow. It's got two systems. System 2 is the slow, deliberate planner. It gets a command like pick up the red block, and it figures out the steps. But then you have System 1, which is like the robot's reflexes. It's the fast executor that turns those simple steps into smooth, fluid motions, and it operates at an insane 120 times per second.
So here's how all those pieces fit together. The model takes in three things: what the robot is seeing, the text command it's given, and its own physical position. Our trusty VLM fuses the image and the text into one unified understanding. A transformer then processes all of that and plans out the actions. And finally, an action decoder translates that abstract plan into the exact commands for that specific robot's body.
And that last piece, the action decoder, is absolutely the key. That's what makes the model a generalist. It's the part that can be swapped out or fine-tuned for a five-fingered hand, an industrial arm, or any other kind of robot. It's what allows one powerful brain to control many different bodies.
You know, a really good way to think about this is to just compare it to language models. GR0T is designed to be the base llama model, but for the physical world. It's a huge, powerful foundation model for action that can then be fine-tuned for thousands of different robots and millions of different tasks.
So when you pull it all together, you can see these three core principles that are making physical AI a reality today. You've got the data pyramid, which is how we're solving the massive data shortage. You've got the dual system architecture, which combines slow, careful planning with fast, reactive reflexes. And you have the generalist model, which creates one powerful brain that can learn to operate all sorts of different bodies.
So really, the question is no longer if AI is going to step out of our screens and into our world. That's happening. The real question for all of us is, as these machines start to navigate our homes, our hospitals, and our factories, where do we think they should lend a hand first?